Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This is the 10th installment in the Adventures with Python series, in which we learn Python by building a text adventure game. No prior programming experience is needed, but you should watch the series videos in order. I'll link the playlist here and in the description. Let's get started. In the last video, we designed and implemented a class to represent inventory, and we modified our game to use this class instead of a dictionary data structure for all of its inventory functions. In this video, we're going to add another class that will work with our system. This class has features we didn't see in the inventory class. I wanted to create two classes for you in this video, but I'm going to have to put off the second class until next week because this video will be too long if I try to talk about both, and I don't want to rush through difficult content. There's a lot to object-oriented programming, so I'm going to discuss various features using different classes in this game as examples. The class we're going to add to the game today is location. This is another example, like inventory, of something that's fairly concrete, so I think that you could take a look at what we currently have in our game and sketch out a class diagram. Remember, a class is data and operations on that data, and objects are specific instances of a class. A class is a type definition. An object is a variable. Examples of specific location objects in My Little Dungeon are cloister, library, garden, kitchen, storage room, and church. Pause the video and see what kind of class definition you can come up with for location. How do you do? Here's a class diagram with my idea for a location. I have a class level field, which is a constant called direction names. Class level fields are shared among all objects of a class. That's useful here because we don't need to have a separate copy of this constant for each object. It would be a waste of memory. But we want to keep it with this class because it's related to movement among locations. Another use of class level fields is to keep track of data that all objects of that class might contribute to. For example, suppose I had a class level field called outdoor visits, and that class level field starts off at 0, but every time the player visits an outdoor location, that location instance increments the outdoor visits field. And maybe if the player goes outdoors some threshold number of times, they attract unwanted attention, or they gain an outdoor explorer skill, or they get a sunburn. The point is that the class level field is shared among locations and they can all access and modify the same field. Now this is in contrast to object level fields, where each object has its own copy of that field. My location class has 5 object-level fields: name, description, numVisits, exits, and inventory. When we create location objects, each one will have its own copy of these fields with its own data in the fields. I have 10 methods: init, a private method called getExitString, and then public methods getName, getLongDescription, getDescription, and getInventory, addExit, go, and then the serialization methods toJSON and fromJSON. I want to stress there are many different ways to design a class. This is one possibility for an object representing a location. It's not exactly the way I designed location in the completed game I showed you in the first video, and it might not be the design I use in the final version of this game, since I haven't designed the final game yet. If I do change it for the final game, you'll see how and why I do. Now let's take a look at the implementation. After we look at my implementation, if you haven't implemented your class yet, I urge you to make any changes you think are important, and then implement your class for practice. I'd love to know what differences there are between your location and mine. Drop a comment below with your ideas. The first field is the class level field, the constant direction names, and you can see this is underlined in the class diagram, which indicates that it's a class level field, and it has a dash in front of it in the diagram, and is named with a leading underscore, which both indicate it's private. Notice it is defined in location at the same level as the methods. That makes it part of the location class, not an individual location object. So that is how you define a class level field in Python. This is going to replace the parallel lists from our game that we were using to convert direction letters into words in the getExitString function. The location will be responsible for generating the exit string, so I've put this data structure inside location. And a dictionary will be much more efficient than parallel lists for matching a letter to a direction string, costing only a constant time to find the string associated with a letter versus having to search the list sequentially for the letter. So I've chosen a dictionary rather than our original parallel lists. If we look at the fields of a location object, we see some basic data types like the name and description are strings, and the number of visits is an integer. But then we have an inventory, which is of the inventory class, and we have exits, which is a dictionary consisting of string location object pairs. That would look like, for example, n as a key, and then another location object as a value, such as the location object representing the church or storage room. This illustrates two ways that classes or objects can relate to other classes or objects. The relationship between a location and an inventory is a composition relationship. The location always has an inventory, and the inventory doesn't exist apart from the location. When a location object goes away, the inventory goes away with it. A location has a part that is an inventory. The location object references to other location objects is called a navigation association. Not because it involves navigating around the map, though, because one location can send a message to another location through that association. Send a message means invoke a method of that object. You need a variable referencing an object to send it a message. For objects in an object-oriented system to accomplish work or fulfill system responsibilities, they need to send messages to each other. So they need to have references to each other. But they don't always contain each other. If one location goes away, that doesn't mean the location objects it references through a navigation association also go away. They might still exist in the system. To design the init and serialization methods, I had to keep this navigation association in mind. If you picture it, each location could have references to several other locations which are also referencing each other, like a spider's web. How do we create that web? We want to give as much responsibility as possible to each object for its own data. So it's best if each location reads itself in from a JSON, as in when we load the original dungeon. So in a loader class or function, we'll create each location, which will execute its init method. And then we'll send it the from.json message and pass it a dictionary from the JSON file. The init method, therefore, doesn't do much. It just makes an object with empty strings a 0 and empty dictionary for exits and a new inventory object with no items. The from.json method will fill in those fields from the dictionary parameter, all except the exits. This is the tricky part. We want the exits to reference other location objects that may not have been created yet. So we must load the dungeon in two passes. In the first pass, each location will fill in all of its fields from the JSON, except the exits dictionary. In the second pass, the loader will send each location object the add exit message for each exit from the location, passing in the direction and the location object that the player will move to if they exit in that direction. Serializing with to.json is significantly easier. The location writes its strings and ints out directly. For the inventory, it sends the inventory the to.json message and adds that into its own JSON dictionary with inventory as a key. Note, it was doing the reverse when reading in, sending the from.json message to its inventory field. For serializing its exits, it's going to create a dictionary of the direction string as key and the name of the location as value. The dictionary is what the loader will use to send the add exit messages when loading back in. The other methods are hopefully pretty straightforward. GetName and GetInventory simply return the name and inventory fields. GetDescription is almost identical to the code from our program, builds up either a lengthy description or a brief description based on whether the location has been visited before. The getLongDescription method is to accommodate the look command, so that always returns the lengthy description. The getExitString method is also taken almost exactly from our program, but notice that I've made it private. I've named it with a leading underscore. When a method is private, it's a helper method to other methods in the class, but isn't meant to be invoked by any part of the system outside of this class definition. In the prior video, I gave you an heuristic for figuring out public-private visibility. I said, for now, fields are private and methods are public. We can improve on that by saying the implementation is private and the interface is public. To decide what should be in the public interface, we think about what services other parts of the system will need from objects of our class, and we design a set of public members, usually methods, but it could include fields, that provide those services. And we guarantee that those public members won't change, so the systems that use our classes won't break if we change it. A USB port is a great example. The plug you use never changes, even though the chips and circuitry behind it evolve constantly. That's public interface versus private implementation. Another example is the Python dictionary. The way we use dictionaries hasn't changed, but the internal implementation was improved in Python 3.7. Code that used dictionaries before 3.7 wasn't broken because the public interface didn't change, but the way they work behind the scenes is completely different. We also want to ensure that users of our class can't break an object by using the services we provide. I will give you an example. The inventory field is private. It references an object of the inventory class. I allow access to the inventory through a getInventory method, but I don't allow access to the field itself. What's the difference? If I allow access to the field, a programmer could change the inventory field to point to a different inventory object, thereby swapping out the inventory at a location. Or worse, they could make it reference a different kind of object entirely, like a string or another location. That will break my getDescription method, for example. Allowing that access could break my class. Letting them access the inventory itself by giving them their own reference is safe because the inventory has also been designed with a safe public interface. The only method we haven't talked about is go, which increments the numVisits field and returns the location object the player will move to if they move from this location in the direction passed as a parameter. This is using the get method of our exits dictionary. What the get method of a dictionary does is returns none if there isn't a location in that direction. So if the player tries to move north out of a room that has only one exit to the south, this method will return none. Now, there's a little kludge here because I'm incrementing the number of visits for every time the player tries to leave. If they keep bumping into walls, the number of visits is going to ratchet up. That's okay for now because I'm only using it as a boolean, have they visited or haven't they? In my final version of the game, I may want a proper count, so I'll have to add a visit method that increments that count and possibly does other work. But for now, this works. Below this class, as with the inventory class, I have some unit tests. They're not exhaustive, but I wanted to test that the basics were working before I integrated this into the program. This code, as always, will be available in my GitHub repository. There's a link in the description. Now, I've already written shabbyabby v10.py that uses this class. Let's look over how it's changed. First, I had to change the abby.json file. The exits for each location are written out as a dictionary of direction string and name of the location the player will move to. So exits for the cloister are n:church, s:kitchen, etc. I need to be sure to match those names to the names of the location dictionaries. In the program, when I read this in, I'll be finding the actual location objects. So each location object will have a dictionary of exit string location object pairs. We will look at how we do this in loadabby. At the top of the program, I'm importing both the inventory and location classes. Note that I named those files with lowercase letters, so it's from inventory, lowercase I, import inventory, the class name, uppercase I. In the last video, I named the inventory file with an uppercase I, and I think that was confusing and not very Pythonic. And I've removed the direction string constants and the getExit string and getDescription functions because those are part of location now. Now they're encapsulated in the location class and not cluttering up our main program. Let's jump past the save and load functions and look at the main game loop. The data that I'm reading in is a dictionary with 3 parts, as before: current location, player inventory, and dungeon. In the last video, player inventory became an object of class inventory, and now current location is an object of class location. The current location variable is therefore a location object we can interact with. The dungeon is a list of location objects. We never use that in the gameplay, but we'll read it in and write it back to the JSON file in case those locations change. I'm going to talk about that more in a moment. Our command processing becomes a little easier. We can directly send messages to the current location. So, for example, in the movement processing, we send the go message to the current location, along with the direction the player wants to move, and we get back the location they're moving to, or none. We'll then check if it's none, and if it is, we'll print a message there's no exit in that direction. If they successfully moved to a new location, we set current location to that new location object. So current location is a reference, a variable that points to whatever location object the player is currently visiting. Each location knows what the next location is based on the direction the player moves. Movement is therefore very decentralized, and the only thing the game loop needs to keep track of is the current location object. For look, we send the getLong message to the current location. For take and drop, we get the inventory from the current location object to send to the inventory swap function. Now let's look at serialization, because our decentralized control structure requires a little more work to set up. First, let's talk about what we have stored as internal data for the program to use versus what we're writing out when we serialize. That will make understanding load Abby and save Abby much easier. Internally, I have a dictionary that I've called data here in the main program, which has 3 keys: current location, player inventory, and dungeon. The current location is a reference to a location object. The player inventory is a reference to an inventory object. And the dungeon is a list of location objects. What I write out is the name of the current location object, a serialized inventory for player inventory, so just exactly what toJSON returns for an inventory object, and then a serialized list of locations, which you got a glimpse of in the abby.json file. Each location in the program, when it's running, has references to other locations. For example, the church, garden, library, and kitchen all have references to the cloister. They all reference the same cloister location object. We want to write that once to the file, but when we read in, we want all of those objects to reference the same cloister location. So when we write out a dictionary of direction location name pairs. That's easy to create. That dictionary is created in the location object's toJSON method. So save Abby is a relatively easy function to write because we just create a list of serialized location objects, and we get the name of the current location and save that as current location. But load Abby is trickier. We need to load the Abby in 2 passes. We read the JSON file into our data_in variable and pull out the player inventory by creating an inventory object and sending it the from_JSON message with the serialized data. We then iterate through the list of location data in data_in and create a location object and send it the from_JSON message with the JSON data and store that location in a dictionary keyed by its name. That gives us our dictionary of location objects. But they're not complete. We haven't connected them to each other yet. We can't do that until they exist. So as we read them in and create them, we create 2 temporary data structures. The first is a dictionary of location name and the exit dictionary for that location, and the second is a dictionary of location name and location object for that location. We then make a second pass through the location name exits dictionary, and for each exit, connect the actual location object to the exit using the add_exit method of that location. We use the location name location object dictionary to do this. So take a location name and exits dictionary pair, such as church and cloister, and look up what location object church is in the name location object dictionary. Then for each exit in the dictionary, in this example there is one, cloister, find the location object for cloister in the name location object dictionary, and send the add_exit message to the church object and pass it s and the cloister location object. Now the reference to the cloister object is in the church object's exits dictionary. We can then get the values from the name location object dictionary and put them in a list to return as the dungeon component of our data structure. Again, this isn't used, just written to and read from the JSON file in serialized form. Now, one other thing we should talk about is what happens when the player changes a location object, for example by taking an item from its inventory. When this is saved out to the JSON, the modified data is saved. This might feel a little bit like magic. Here I have a simplified behind-the-scenes picture. Let's pretend we have a dungeon with only 2 rooms, the cloister and the church, and there's a book in the church. Now, I have a list of location objects that I read in initially. I never use that in the game loop, but it always contains up-to-date information. How is that possible? And the TLDR is it references the same location objects as the location objects in each location object's exits dictionary. To understand that, it's important to distinguish between an object and a reference to an object. An object is data in memory. A reference is a variable, and we can have many references to the same object. So if I change an object using one reference, it's also changed for the other reference. In my image, you can see my list. And again, I'm only showing 2 locations. And you can see that it references the 2 location objects, which I've greatly abbreviated here. And each location object also references each other. And they each have an inventory object of their own. I'm also showing player inventory, and I'm showing current location as referencing the cloister object. Suppose the user chooses to go north. Now we ask the current location, which is the cloister, where the player ends up if they go north, and it will return a reference to the church object, which we store in current location. Now the player takes the book, and we get a reference to the inventory from current location, so that's the church's inventory, and we swap the item into player inventory. And then say the player goes south, so we ask current location, the church, where the player ends up if they go south, and it returns a reference to the cloister location object, so current location now references the cloister object. If we then save this, you can see that the inventory that's referenced in my list has been changed, even though that's not the current location any longer. And we never interacted with the list at all. It contains accurate data. To write this out, we'll get the name from the current location, and then we'll serialize all the objects in the list, and we'll serialize the player inventory, and our entire dungeon is preserved. Does it seem like magic? Giving agency to objects can feel very strange when you're used to functionally decomposed systems. But if we design it correctly, each individual process is not difficult to understand. I found writing the serialization functions the most difficult, and that is why they're so heavily documented. I first figured out what my game needed to operate, and then what I'd need to store to read the dungeon back without losing any data. I then wrote out the format of the serialized data and the format of the data I was storing internally in the game. Once I'd done that, it was just a matter of transforming it from serialized to internal and back. Not that it was easy, but figuring out what I need and documenting it carefully made it straightforward. To practice, I recommend you add a class-level variable to this game. It doesn't have to be how many times the player has visited an outside location. You could document how many times they pick things up. Maybe they get stronger, or maybe the dungeon gets mad it's being stolen from. I don't know what the consequences are, but you can write them into your game. You could also take your monster game and add another class to your monster game. For example, you could write an inventory for your monster and allow it to swap out armor or weapons. A monster inventory relationship would be a composition relationship. The inventory is part of the monster object. You could create a team object composed of monsters and allow monster teams to fight other monster teams. Or rewrite this system from what you remember, or with your own version of the location class. When you're feeling even more confident with writing your own classes, join me for the next installment of Adventures with Python. As always, have fun and keep coding.